Okay. So this right here would be the problem that we just talked about. That was up on the board there. And we're doing part A here. And so what we're going to want to do is the first thing we need to figure out is what is the saturation or equilibrium in that solution, right? So we need to use our lead PbI2 here, dissolving, which is the KSP, right? So we calculate out our KSP. We find our KSP from the table. Does everybody understand how to get these KSP formulas? So in this case right here, because we would have right? And so our equilibrium constant is P equals products. And then we don't divide it by it, right? Because this is a pure solid. Okay? Okay. So all this right here is the rearrangement of that, right? I've divided over the I because I need to figure out how much lead I have to work with in this solution. Okay? Because you notice the common theme between all of these is I have lead done. Okay. Now, one of the factors you have to keep in mind here is see this number here for KSP? It's a very small number, right? And so what is the major source of iodine in this solution? It's going to be the addition, right? That addition number we have. So the 0.001 number right there. Okay. Now, the Pb2 plus is still going to be dominant in that solution because it's actually going to be a slightly larger number, right? Okay. And so we're going to come down here and we're going to take each of these species. We would then look up their constants. In this case, are these solubility constants, solubility products. They'd be formation constants, right? Yeah, because we're actually forming complexes. Okay. Now these are the different water-soluble complexes of lead with different iodide amounts. The lead 2 plus. Yeah, that one will be solubility. Okay. Because that's how much of the solid lead dissolves in the solution. Okay. Okay. And so that's 7.9 times 10 to the negative 9. That's the KSP divided by the 0.001. That's from here. That's squared because of the power of 2. Because you have 2 iodines that would come off of this, right? Okay. We do that calculation. We get this number out right here. Okay. All right, everybody good with that so far? Okay. Okay, now that lead 2 plus, that's actually a larger amount than the iodine minus. Okay. And so we're going to come down here now. Next thing we're going to do is, well, each of these complexes will form. This is actually the equilibrium constant solved out to get the one we're trying to solve for on one side. Okay. So if you were writing these out, they would be K equals products of reactants, right? Everybody okay with that so far? Okay. Anybody getting lost there? This would be the formation complex for this right here. So you'd go to that table, you'd look up the lead iodide plus. Okay. And so that's a complex that's being formed in this. It is soluble. And this would be that formation complex equilibrium right there. So the equilibrium complex for forming that complex. Equilibrium constant for forming that complex. Okay. So now we take our numbers. This is that K right there. Plug that in. Then it's going to be multiplied with this number here, which is the lead 2 plus. Note that technically this number is actually gathering errors when we do these things. Okay? So this one here, notice how we're doing the largest number first, then the second largest number, then the third largest number in terms of our K values. Okay? Can everybody see it okay? You always want to go down from your largest equilibrium constants down to your smaller ones. Because the largest equilibrium constants means you make the most of it at the end. Okay? The smaller ones are actually going to make less of them at the end. Right? If you have large enough equilibrium constants that they make a large enough product, you could consume almost all of your lead here. Okay? Now in this case we have excess solid, so it's not really going to matter. If we did consume excess lead, what would happen? So let's say we have an excess, right? So we have a warehouse over there. It has 1 billion staples in it, okay? You use up a pack of staples. Is the next person going to be like, I have no staples? No, you're going to just draw some more from the warehouse, right? And so you'll just keep drawing more of the solid lead into solution in this problem, okay? But if you ever have it where it's not saturated, that's going to matter. Like this amount that we made here, that would consume the lead, right? So keep that in mind when you're doing problems where it's not saturated, okay? Okay. So in this case, we can just plug our numbers in. We have the iodine right here, and then we have the lead number right there. We plug these numbers, we get this for the answer, and that's the answer of the concentration for the PbI+. Everybody okay with that? And we literally just do that for each of these. Keep in mind, whenever we do these, the number of iodines here is changing, right? And so the power changes for the chemical formula. If you have to, you can write out the chemical formulas for them. It'd just take you long, okay? Everybody understand why these powers are going to 3, 4 here? And where I find that? It's that number there, right? Okay. Okay. Did I lose anybody in any? Mm-hmm. You okay?
Yeah, sir. Trying to find big one.
So, does anybody happen to have that up? No? Does anybody have your book? So if you go into the appendice, I believe it's appendice F, if I remember correctly. It's the formation constants. Which one is that? I. Okay. Here. Exit out. You'd look it up. Bring your book by and we can try to look it up, okay? Typically what I do when I'm trying to look them up in the book is there's a search function.
Yeah, I tried.
Okay. If it came up with nothing, then the formatting's the problem. Okay. So, does anybody have any other questions on how to do these problems, assuming you can find the equilibrium constants? Okay. Okay. Let's real quickly look at the 1 molarity one. Now, when you're looking at 1 molarity for this, what you notice is that when you start looking at these numbers, that lead number is minuscule compared to 1 molarity iodine, right? Okay. And so you're going to plug these into the same formulas. And what you're going to see here is that you're going to end up with a lot less lead 2 plus. See that? Because it's going to consume a tremendous amount of the lead 2 plus. Right? So does everybody want to try those numbers real quick? I'm going to leave it on this page real quick so you can use the numbers. Remember, it's for 1 molarity iodine now. Oh, sorry. There. It didn't come back up when I hit it. Yeah. So you're going to be doing this with a concentration of 1 molarity for the iodide. And I'll give you till 25. Please just try to get as far along in the work as you can. You'll notice that that first step in this A problem, we didn't force that equilibrium back that much. We didn't do a lot to that first equilibrium. 1 molarity does a lot to that equilibrium, doesn't it? We force that back significantly. By the way, this is actually how like a real stream would look, or a real world solution. I know back in Gen Chem 2, you probably thought everything was in the form of like calcium 2 plus, lead 2 plus, and just floated around like that. It doesn't. It floats around in a variety of complexes. Okay, so we literally just do the same problem again. The big difference here is we're going to be doing 1 molarity here, right? For this. So when we plug 1 molarity into here, this number becomes much, much smaller, i.e. the KSP, as 1 squared is. Okay? So that lead 2 plus number, all of a sudden, it becomes the KSP number. Okay? Okay. And that means all of these other numbers are going to go down a little, but not as much as you might think. Wouldn't they go down as much as you might think? Anybody have any ideas? See, like that goes down, but it doesn't go down these orders of magnitude, right? And the reason it doesn't go down as much as you think, remember that you are multiplying by that iodine concentration in each of these, right? Okay. So a fun little issue is you actually can just take out this iodine term in all of these calculations. Because it's 1 squared, 1 to the third. Mm-hmm. Mm-hmm. To A. That's to part A. Yeah. And then part B, which was the one we were doing just now, was using concentration of 1 instead. What are you? Yes,
Yes.
the stone here. Okay. Yes. So this was literally K equals products of reactants. And then we just solved it for the product, which is what we want. See that? It's literally, I took this number here, divide over, right? Yeah. Product right here. These are reactants. Take reactants, multiply over. And so I get K times my reactants. So real quick, we would write for the equilibrium constant, K1 equals, and again, it would be product. It would be PBI2, I1 plus. That's the first power. And then it would be reactants, which would be PB2 plus. There's only one of those in this, so it's just to the power 1. And then it would be I minus. And there's one of those in that one, so it's just power 1. And so if you multiply both sides, right? So these cancel. And we get our formula up there.
So K1 is unknown.
Okay. So you're comfortable with this part right here, right? Got our formula. Okay. So K is something you can look up. The equilibrium constants are the thing you look up in the table. Yeah, I mean, all the Ks are here. All of these are equilibrium constants. The specific ones are going to be for formation complexes. So there'll be formation constants, complex constants, and up there we have a KSP, which is solubility problem. But they're all equilibrium constants. Okay? A Ka would be an equilibrium constant, a Kb would be, they're all equilibrium. Okay? Okay. And so the only thing you don't know is the Y. The thing we have by itself. That's why we got it by itself, right? Is so we can solve. Okay?
I think I just
Okay, so in these cases right here, these would be from your book. You'd look up all these. That's why it was tabulated together. So you can know to look them up for easier. These would be the concentrations we got there. These right here are the concentrations we are given in the problem. And we don't know these. And then that's why these are just listed right here. Like, you have that back. Because it's in the book. It's tabulated. Okay, did that make sense? Okay. Anybody have any questions about any of this? All right, we're going to go ahead and move on then.